Okay, folks, we're gonna share the screen here. Look at this one over here. Share it. All right, so let's talk about water requirements. Um, I think that most of our population does a pretty good job with water requirements now. There's a couple of studies ongoing back east. I think it's North Carolina. Might be wrong there. It's a multiple site one, but I think they're heading it out of North Carolina, where they're looking at dehydration and water intake, and they're finding that people are having just as much trouble with too much water. So we'll look at that here in a second. So you're going to see different percentages depending on the size of people. So typically 60% of 60% of you, if you're a male, is water, and it's broken down here. And females typically 50%. So those can change, right? If you're a larger person and you're carrying more adipose, and so the fat cells have a lot of water, you could be a little bit higher. I've seen as high as 70. I'm not sure about that. I've seen it as low as 55. So 60 is a good range, 50 for females. Obviously, it's about mass and size. So there you go. The main component of the water and the need is for thermoregulation. Our bodies put off a ton of heat. So if we measure that heat in watts, at rest, we're putting off about 70 watts. If you want to know what that is, find a 60-watt light bulb and touch it. And I think that you'll find pretty quickly that 60-watt light bulb gets pretty hot. In exercise, when your heart rate's up 80 to 90% of your max effort, your VO2 max in this case, you're throwing off as much as 100 watts, or I'm sorry, 1,000 watts. So if you calculate that, right, if 70 watts, if we stopped regulating temperature, if we stopped evaporating it off or radiating it off our bodies, and we held on to that heat that we're producing every second that we breathe in and out and contract muscle, it would increase our temperature at a rate of almost 2 degrees every 4 to 5 minutes. So if your normal temperature is 98, yeah, so 4 to 5 minutes later, you're at 100, 4 to 5 minutes later, 102, and you can see the pattern. It doesn't take long before you're in a state that will ultimately kill you. And that's what, when we talk about heat stroke, that's what heat stroke does. Just a quick story. Last weekend, I was at an event, and a young man had been ill and participated anyway, and had heat exhaustion, and he did fine. He was having a hard time recovering. He normally is one of the better athletes out there, and he was having a hard time recovering. And then he started to shake. Then he started getting the chills really bad, and things started to just kind of shut down on him. Even though he was starting to intake water, he was so far behind that his body was starting to have some severe problems. He did fine. He was able to, as long as you can take in the liquids, you should be fine. If you can't, then you have to go get an IV, and they put the liquids straight into your veins. But he was able to digest, absorb liquid, so he did just fine. But it was really scary, and that had to do with how much heat. Now, he went into a protective response where his extremities, he stopped sending as much blood out to his extremities, and that's why he was getting the chills. It was coming in and trying to protect his vital organs. That's why he was getting the chills. It was really kind of scary. Anyway, remember this: we put off a lot of heat, so even at rest. So you can imagine what we're doing during exercise. So when that being said, understand why we have the water requirements that we do. It's regulated in our hypothalamus, and our body does a really good job of self-regulating. Thank goodness. We don't have to think too much of it. We tend to burn right around 98.6 degrees. That's where our body gives off just enough heat and to keep us right about that temperature. When we're exercising, we may burn a little hotter, somewhere around 100. That's pretty normal. So if you have an athlete who's not feeling well, they come in right after a practice, or they come to your home if it's your child and they're hot, it just could be that they've been exercising. So understand that. We don't want to get above about 104. That's when problems start to happen. So Once again, our core temperature is regulated by our hypothalamus, which sits in our brain. There's a little picture of it right there. And this is how it's done. Basically, it's a balancing act between what our hypothalamus is sensing for hot and cold in this case. This does the same thing for blood sugar, all kinds of things. Our hypothalamus is a regulator. So that's really its purpose. And you can read through the slide and how it does it. Basically, if you're too hot, it vasodilates to get more blood to your extremities and opens up those capillary beds so we can give off more heat through evaporation, which requires water. We can also radiate it off because it's closer to the surface of our skin. We like to put wet towels over our bodies and get some conduction to work. We also like to fan ourselves, right? Or sit in front of a fan, that's convection. So there's lots of different ways that we can increase the heat loss. We can also do the same thing if we're too cold, right? Our body our hypothalamus tells us to vasoconstrict. We start to bring that heat in towards our core, and we warm up. So it goes both ways. And in this case, we're talking a lot about getting off heat. So we're talking about vasodilation. So here's one of the ways we can do it. Evaporation is one. I just mentioned it. It requires water. And if you look at the picture, this person is sweating. Sweating is not the same as evaporation. It's a consequence of it. If you're in humid conditions, or if your evaporation rate is high and the evaporation starts to condense in your hair or on the pores of your skin, then it can condense and join together, and that forms a ball of moisture we call sweat. So that's how sweat happens. And so oftentimes we can have a sweat rate, but that only begins once you start sweating. We're evaporating all the time. If you put your hand on the top of your head, right, and you kind of find a spot where you don't have a lot of hair, or on a part somewhere, you'll feel it hot. It'll feel hot. So that heat rises and it likes to go out the top of our head. So which makes sense as to why we have a lot of capillaries on our head and on our face. If anyone's ever had a cut on their hand, a small cut, it doesn't bleed nearly as bad as a cut on our face of the same size. When we look at sweat rates, and that's because of the capillaries in our face and skull. Because heat rises, we try to get it out of our bodies. We have a lot of capillaries up in our head and our skin and our head. Okay, sweat rates: 2 liters an hour. Think of what a 2-liter bottle looks like. So that's a lot of sweat. Now, understand that this is at during exercise at a high rate. Once again, this is just counting the sweat. This is the condensed evaporated moisture on our skin. So it's a lot. It's quite a bit. So if you think about how much we're putting off, think about how much you need to have in your body. We can also radiate, convect, and conduct. Radiation is just the release of the heat without the assist of a water molecule. This is the way we feel the temperature from the sun, for example. Convection is like if you blow a fan on you, or if we stand in a cool breeze. We call it a cool breeze because it's blowing the heat off of us. Conduction is when we do it from surface area to surface area, or in this case, between two mediums, if we talk about it in physics. I like to demonstrate this by putting your hand on the desk or something in front of you, anything in front of you. And if it's colder, it means that you are conducting heat into it, and you are feeling the cold from that. Now, if you keep your hand on that thing long enough, if it's a computer screen, that's one thing, it's producing heat itself. But if it's a desk, you'll eventually have the same temperature, and it won't feel cold anymore, and that it'll balance out, right? So that's conduction. So those three are the other ways that we can get rid of the heat. If you want to see an example of what that looks like, here's a bicycle rider, and you can follow the arrows and kind of see how he's getting the heat off his body and absorbing it, by the way. So it's kind of a constant battle. That's why it's difficult to regulate athletes' temperatures in hot, humid conditions, because it changes the environment, and our body just doesn't work as well putting it off. So we have to use things like convection and use fans on the sidelines for football players, or turn the temperature down, excuse me, in the gym, things like that. Okay, so here's one that you need to pay attention to, acclimatization. So our sweat rates are regulated by our hypothalamus. Our hypothalamus likes this thing called a set point, and we like to regulate at what our bodies are used to. So as soon as we change the environment, we have to acclimatize to that environment, whether it's altitude and we have lower pressures, or if it's heat, or if it's humidity, all of those things we have to make adjustments to, or cold or hot. The way that works is you have to be in that area for, it depends, right? The more severe the change, the longer you have to be there, up to 7 days. So if you're going to hike to the top of Mount Everest, you need to spend at least a week at high altitude so that your body gets acclimatized to that high altitude so you can make the last push. That's an extreme. If you were just going to go to Flagstaff, Arizona, which is, about a mile high, you may not need to stay there a week to acclimatize, but you probably should be there a couple of days. With that being said, your rate of work needs to be adjusted as well. So anything above 70% of your VO2 or your heart rate is where you need to be. So I'm going to ask this question on the quiz, so pay attention. Up to 7 days at 70% of your max. Up to 7 days, 70% of your max. So that's how you acclimatize. And that's in whatever environment. 7 days in the cold at 70% of your max, 7 days in the heat at 70% of your max. That's how you get there. All right. This is just a video. I think it's attached. If not, it's on YouTube. You can just type in what happens if we stop drinking water. And it just goes through the process. Basically, we lose the ability to give off heat and other important metabolic issues. So, all right, effects of dehydration. Another question on the quiz. 2% loss in body fluid is considered dehydrated. You'll have decreased blood flow, sweat rate, heat dissipation. Your core temperature will rise. You'll increase the rate of glycogen use, right? So just like an engine in a car, right? If you limit the amount of oxygen, you have to throw more fuel in there to get the piston move the same. So if you have plenty of oxygen, it works just fine. It's the same thing with water in our bodies. If we have plenty of water, we work more efficiently. We don't have to use as much glycogen. This is a good slide to remember, 2%, and then that list of effects of dehydration. Here's some more effects. This is what we're looking at percentage of body loss. So how do we do that? Well, you measure yourself before and after. There's a great resource called Gatorade Sports Science Institute, or the GSSI. Once again, Gatorade Sports Science Institute. Please look that up. It's got some great stuff on hydration. Gatorade, I know that they're a big marketing company. That's fine, but they do some great research, and the GSSI does a great job of putting that material online for people. So take a look at that. A lot of the information I get for this class is based off of the GSSI. So a lot of independent studies in there. It's not just from Gatorade. So a lot of independent studies that they've taken and put in. They have a library on that site that you can look at peer-reviewed articles that are really, really good about dehydration. Here's some effects of dehydration. You're going to be thirsty, obviously, impatient, nauseous. Now, if you look at this list, it looks a lot like a concussion. So in my world as an athletic trainer, I have to be very careful that if I'm looking at a brain injury, I also know what their sweat rate, what their intensity of work, and how much fluids they've been drinking. Sometimes that's hard information to get from an athlete who has these things going on. But once again, it mimics a lot, and dehydration and concussions go hand in hand. If you're dehydrated, you run a higher chance of concussion, just because of what your brain sits in. Yeah, sits in a hard skull, and if you're dehydrated, you have less fluid around that brain, and so your brain's smashing up against that hard skull. So it's interesting to me, and not terribly surprising that the effects of dehydration and the symptoms of a concussion look a lot the same. This video here is on Gatorade Sports Science Institute. If you download these onto your computer, you'll be able to open this and watch it. If you do it from just just opening off canvas, it won't work. You actually have to do a full download. But basically how this works is that you're going to weigh yourself and the fluid and everything you're wearing, right? And so before you work out, and then estimate what you've had to drink, and then put that back on the scale. So if you only drink half that water bottle, it goes on the scale with you. And then of course towel off, because you want to get the moisture off of you. And sometimes your shirt gets really heavy, and so that throws it off a little bit too. But basically, you're going to weigh yourself before and after a workout and see what your weight is. If it's below 2%, you obviously need to drink more in your workout. Here's the key to the idea of tracking your sweat rates, and you just do that by weight, right? You're just looking at your weight before and your weight after. You can have, if you look at what your temperature and humidity and your environment is for those workouts, and that's listed on the same page, you'll have a pretty good idea of how much you need to drink per condition. So if you're an athlete doing triathlons throughout the year and you've trained for 6 months, you should have a whole book full of, hey, this is what I need to drink at 80 degrees and 80% humidity at this elevation. So you can get that technical. So you'll know what your sweat rate is, and so you're not over consuming water or under consuming. You'll hit it right on, which is really good if you're an elite athlete and you're really trying to dial in your sweat rate, so you're not carrying extra water weight with you or underperforming because you're dehydrated. So you can keep a hydration log with sweat rate or how much you weigh before and after, environmental conditions, and heart rate, and work efficiency is basically what that's called. So it's a pretty good thing to do if you're working with elite athletes, or if you intend to be that scientific about your workouts. All right, just some recommendations. Here they are. This is for athletes. So we anticipate that they're going to be doing some sort of exercise. That gives you an idea. Here is a slide for how you can do that leading up to an event. 2 to 3 hours just before and then after. These are from Gatorade Sports Science Institute. I'm sorry that picture is in the way. Basically what it says is water with electrolytes, so you can get some Gatorade. Hyponatremia, I mentioned before, this is water intoxication. This is becoming more and more prevalent, and you may not, if you're drinking a gallon of water right before an event, as opposed to drinking it throughout the day leading up to the event, you could get hyponatremic. And basically what you're doing is you're over volumizing your cell. So the electrolytes that may be contained in that cell are further spaced out, and they may not be able to interact with the material or organelle or whatever that they need to react with in order to make you perform better. So hyponatremia can be an issue. And when we look at issues with hyponatremia, which if you look at them, right, weakness, muscle incoordination, disorientation, seizures, things like that, some of the same symptoms as dehydration. So once again, it's a balance, right? We need to be better at figuring out the balance of water intake and not just say, hey, just drink as much as you can. That's probably not a good policy. I like this picture here. That's kind of the color that your urine needs to be, kind of that soft yellow. And I've had people ask me recently, and I think it must be something going out on social media or something. Should it be clear? Your urine should not be clear. There should be some color to it. It shouldn't be a really dark yellow, but there should be some color to it. That just tells you that you're getting enough electrolytes as well. So you don't want to overhydrate, become hyponatremic, at least mildly, and wash out all of your electrolytes. That's not good for you either. So you ideally should be urinating every 1 to 2 hours. If you're drinking properly, should be pale, and you can consume any liquid you want. Now, water is great, but fluid or water is contained in milk and juices and other things too. So broths. So understand that you're getting fluids from other places. Be careful not to overconsume protein. It requires water to break it down. Consume caffeine drinks in moderation, especially right before an event, because it is a diuretic and it'll wash out what you're putting in. So if you are going to take caffeine for some sort of stimulant before a race, make sure you're taking the drink the energy drink, and then you're drinking water too, so that you're not going to dilute the caffeine. You're gonna replace the water that caffeine is going to stimulate your kidneys of getting rid of. So realize that caffeine is a diuretic. Alcohol is also a diuretic, and it should not be. You should not drink alcohol before. Don't use that as your fluid. That just is just common sense. Okay, so this carbs and fluid video is also off of Sports Science Institute. It just covers exactly what I just talked about, only it shows it in video form, and it talks about carbs as a fuel, and that if you take carbs with water, you're getting, two birds with one stone, basically what it says. Once again, you can find it on Sports Science Institute or download the entire slide bank and you can check it out. Okay, know these terms: acclimatization, 7 days, 70%. You might want to be able to give an example of conduction, convection, evaporation, and radiation. Understand euhydration is that balance between dehydration and hyponatremia. So we want euhydration. That's what euhydration is. Okay. Any questions? Text, email me.